So our next speaker is Alexander Minakov, who's going to tell us about Soliton gas for the modified KdV equation.
Yes, thank you very much. Yes, it's very pleasant to be in this conference. Thank you for this and for the opportunity to share results of the joint work with Professors Tamara Grava, Robert Jenkins, and Ken McLaughlin about Soliton gas. So in this conference, there will quite a lot of talks about Soliton gas, so it will be another one. So we consider Soliton gas for the modified Korteweg-de Vries equation. This equation has this form. And well, okay, so it differs from the Korteweg-de Vries equation. Like the Korteweg-de Vries equation, it has q to the power 1 here. And what is our aim? Our aim is to study an interaction between a gas of solitons and one big soliton, which enters this gas and then it interacts somehow. Yes, and then also we will derive some kind of kinetic equation, which was also derived by other people. So first of all, the modified Korteweg-de Vries equation is an integrable equation. It has a Lex pair representation. It has soliton solutions, elliptic solutions, and also it has some other solutions like breathers and hyper-elliptic finite gap solutions. In this talk, we will be mostly interested in solitons, and in elliptic solutions. So, well, okay, so as many other integrable equations, this modified Korteweg-de Vries equation, it has soliton solutions. So I would like to maybe to highlight some differences, distinctions between solitons for the MKdV and the solitons for the KdV. So for the Korteweg-de Vries equation, well, okay, so I just reminded, well, okay, when q to the power 1, so this is KdV equation. So for the Korteweg-de Vries equation, all the solitons, they are oriented upwards. And okay, so for the MKdV, we have two types of solitons. They can be oriented upward, like a plus. They also can be oriented downwards, when we take here minus. Then another distinction is that the MKdV equation is not Galilean invariant, which means that if you want to take solitons not on zero background, but on some constant background, we cannot obtain them just by some phase shifts and a constant. So solitons on constant backgrounds, they have more complicated form, which is written here. And then also, well, also there are some interesting singular limits of these solitons. For instance, if we take a positive constant and negative soliton, which are oriented downwards, then there is some singular limit which give us some slowly decaying solution of the MKdV. And okay, but in any case, in this talk, we will be interested only in solitons on zero background. And then there are also, well, another fundamental solution which we'll be interested in is the elliptic solution. So it has three parameters in it, and changing those parameters, we can change the form, the shape of this elliptic wave. So this elliptic wave, it oscillates around the level beta 3. Then its amplitude is the difference beta 2 minus beta 1. Then, for instance, if we take beta 3 close to beta 1, then we obtain rarefied wave, and in some particular limit, we can also obtain soliton from this wave. Yes, and then so there is also some spectral parameters associated to this to the MKdV equation via the Lex pair. So we can also look at those solutions like with solitons and elliptic wave via its well, from the point of view of the spectral parameter. So in terms of the spectral parameter, solitons correspond to discrete spectrum in the complex plane, on which discrete spectrum on the imaginary axis, and for instance, a constant, it corresponds to a continuous spectrum also on the imaginary axis, and then elliptic wave, it corresponds either to two intervals on the imaginary axis or to three intervals on the imaginary axis. So they look as genus 1 and genus 2 solutions, but in reality, the genus 2 solution here can be reduced to genus 1 solution. Okay. Yes, and now I will go to some history. So yes, the question which we'll investigate, well, it was investigated by many people. So Zakharov in 1971, he considered some gas of diluted gas of solitons, and well, so there was diluted gas of solitons, and then he derived some equation for the speed of a tracer soliton which goes through this gas of solitons. And well, the key observation for this is that if we have just two solitons, then when they interact, they exchange their phases. So if we have two solitons, so one big soliton, one small soliton, then okay, so first we have a big soliton, then it overtakes the small one, and in the end they look similar as before, but in reality they get some shift. So for instance, if we take some animation, so here we have this big soliton, small soliton, and now if we just fix this position of the small soliton, okay, so we fix it here. Okay, so we see that after the interaction, the small soliton was shifted to the left a bit. Yes, okay. So in this picture, okay, so this is just two solitons. Here we see the speed of the biggest soliton, of the biggest soliton peak. So this the x-axis, well, yes, the horizontal axis it is time, and the vertical axis this is like x. Then on this picture we see the speed of the big height. So first it goes like with a constant speed, then it increases the speed, and then it again goes back to the original speed. And on the fourth picture we see acceleration of this big soliton when it interacts with a small soliton. Yes, okay, so this is written here, right? So when we have two solitons, okay, so this is in the case of the Korteweg-de Vries equation. When okay, so first we have them when time is very large negative, and after they interact, we see that they get some shifts. So the small soliton is shifted to the left, and the big soliton is shifted to the right. Yes, so using this observation, Zakharov derived actually not an equation, but a formula for the speed of the soliton which passes through the gas, right? Because he has diluted gas of solitons, which means that when the big soliton interacts with each small soliton in this gas, they interact pairwise. And he derived a formula for the speed. Also, he had some density function f, and this density function f, it satisfied some continuity condition. Okay, so then Gennady L and okay, he considered not diluted gas, but he considered a dense gas, and then he derived an equation, real equation, right? So because here we have just formula for the velocity speed, so here we have really an equation for the velocity speed. So what we will see in the end of the, well, in 15 minutes, we will see a similar equation which we derived for the modified Korteweg-de Vries equation. Okay, so now I will go to the construction of the soliton gas. So in 2016, Dyachenko, Zakharov, and Zakharov, they wrote a paper where they constructed a new type of potentials. They called it primitive potentials. Then some particular case of those potentials was identified by Girotti, Grava, Jenkins, and McLaughlin as some solitonic limit. And okay, so and here we yes, okay, so here we develop further this approach for the MKDV equation. So first of all, if we have just one soliton, it corresponds to some Riemann-Hilbert problem. So we have 2 × 2 matrix M, which is meromorphic in the complex plane and has all conditions at 2 points on the imaginary axis. And okay, so here we have this parameter gamma, so the point kappa, it determines the speed and the size of the soliton, and the position, the initial position of the soliton is determined by this parameter gamma. So when gamma is large, well, okay, so when gamma is large, then yes, okay, so when gamma is large, then the position is shifted to the left, right? When gamma is small, then the position of the soliton is on the far right. Okay, so then if we want to construct a soliton gas, first we consider Riemann-Hilbert problem for n solitons. So we have n solitons, which means that instead of one pole condition, we have n pole conditions. So now we introduce some scaling parameter n into these pole conditions, right? We'll see a bit later why we need it, but we will need it for well, okay, we will need it for some convergence, because we will use some limit which will tend to some Riemann integrals. And yes, so we see that this scaling, it means that the initial positions of each soliton, they tend to plus infinity. Right? So here is a picture of how we do this. So first of all, we have this n solitons, we have n poles, and they are more or less spread along some intervals, along two intervals in the complex plane on the imaginary axis. So then okay, so here in this original session, we cannot go to the limit n to infinity. Right? In order to go to the limit n to infinity, we first rewrite these pole conditions as jump conditions on loops which surround these intervals. Now, when we are on these loops, we can go to the limit, and so we will have some sum of these pole conditions, and then what we'll get some Riemann sum which converges to some integral. Okay, so on these loops we can go to the limit n to infinity. Okay. And after we do this, we can go back to the original intervals on the imaginary axis. Okay. Yes. Okay. So now I just want to mention that what we obtain in this way, we'll obtain some. Well, okay. So this is soliton gas, which occupies the positive half axis, like more or less from some small positive number to plus infinity, and on the left we have just zero. Well, okay, something exponentially small. So in this way we can add some additional big soliton on the left. And as time propagates, it will move to the right, and well, okay, it will start interaction with each of these solitons, right? It will be, well, okay, it will last forever because, well, it will be faster than any particular soliton, but well, there are infinitely many solitons. On the other hand, we could also modify a bit this construction. So actually, if in these pole conditions, instead of this function theta, we substitute minus theta, it would also construct us some potential for some solution of the modified Korteweg-de Vries equation, but with different properties. Yes, with different properties. So if we flip theta to minus theta, the soliton gas will occupy the negative half axis. So in this setting, if we put some big soliton on the left, it will just interact with this soliton gas just for some finite time, and then it will just go to the right. So that's why we chose this first setting, because now we can study the interaction of the soliton gas with this big soliton for like forever, right? Okay. And so yes, okay. So on the language of the Riemann-Hilbert problem, for the soliton gas, we had a Riemann-Hilbert problem with some jumps on these two intervals in the complex plane. Now, if we want to add this big soliton on the left, we need to impose some additional pole condition at some points of the on the imaginary axis, which are situated here. Like so, they must be bigger. Okay, so the size of the soliton is proportional to the amplitude, is proportional to this number. Like so higher this position of this point, then the bigger soliton we have and the faster soliton we have. And then, okay, so then in the long time asymptotic analysis, if we send 10 t to infinity, then it will turn out that this xt plane will decompose into several regions. So first of all, well, it will be some left region where we will have decay. Then it will be some transitional region where we will have some modulated elliptic wave. And then in the far right, it will be again this elliptic wave, but already not modulated. It will be some stable elliptic wave. And the soliton, it will move through this far right region, right? So it starts here and then it propagates. Well, yes. So there are some explicit constants which separate these regions. Okay. So we saw the picture for the interaction of two solitons. So now we can try to imagine what happens when the soliton interacts with soliton interacts with the soliton gas, right? Okay, so we can see some other animation for this. Maybe I can try to speed it up. Okay, so here we have just regular elliptic wave, and here some transition from it to the zero. Okay, so it interacts. Then, okay, so what we can observe that actually, well, there will be some speed of this soliton, like some average speed, but each time when it interacts with the further soliton, with further small soliton, it will get some additional shift of the position to the right. So it will also, so it will well, okay, so it will be accelerating from time to time. Well, every time when it interacts. So here in this picture we can see similar situation, but when we have negative soliton which interacts with the same wave. Okay, it takes time. Well, okay, so here we see that this peak, it becomes smaller and bigger, right, when it interacts. And also we saw the same for the situation with positive soliton. Yes, okay, so so here we have a plot of the soliton peak of the speed of this big soliton, right? So this is the position and this is time. So we see that the velocity, well, okay, so it's okay, so this is time, this is time, and this is x, right? So we see that it almost linear function, but each time it interacts with the solitons, it gets some well, it gets some local changes of the velocity. Okay, so now I will go a bit to the analysis of this problem. So yes, okay, so actually in the long time analysis of this problem for the soliton gas, we get, well, this analysis is similar to the analysis of step-like problems with durable equations. And so what is crucial there is the construction of some additional phase function. So originally we had this function theta in the Riemann-Hilbert problem. Okay, so in the original Riemann-Hilbert problem we had some function theta. Then when we want to study the one-time asymptotics, we need to change this function theta with some additional function, with some other function phi. which share some properties of the original function theta, but differs from it on some parts of the counter. So those green lines are our original support for the solitons. Then the first situation is when, okay, so those blue lines are curves where imaginary part of this phase function phi equals to 0. Then the first situation is when those lines do not intersect those intervals of the spectrum. So this is the first situation. This corresponds to this stable elliptic wave. To this corresponds to this green region. Then the second situation is when those lines, when they intersect with this interval, with these two intervals. In this case, the analysis is similar to the first one, but so the length of the intervals on which we set up the final Riemann-Hilbert problem, it will be a bit smaller. So that's why we get this modulated region. Okay. Yes, so actually those problems, they are very similar to the problems which appear in the long-time asymptotic analysis for the MKDV or for the KDV equation. They were studied like by many people. Also, okay, by the previous speaker, it was studied for the KDV equation. And well, okay, so we obtained some formulas. And well, okay, so in this Riemann-Hilbert problem, so we need to construct some area parametrics, some around those points, some maybe Bessel parametrics around those H points. But in any case, this is not where we get position of the soliton. So because the position of the soliton we obtain it when those blue lines intersect this point I kappa 0. So when we are really here, then we get the soliton. And well, okay, so next. There is G function analysis or G function mechanism in this analysis, and well, also as was explained in the previous talk. And what is remarkable here is that so this function G, which is a difference between those two effective potentials, it can be represented in this way as a logarithm of some function rho, and then it's just quite interesting that this function rho, it satisfies kind of continuity condition for the function f, right? Okay, so in the beginning we had some this distribution function f. It satisfied some continuity condition. In this setting, the analog of this distribution is played by this function rho. Okay, so this so v is the velocity of the soliton, is the average velocity of the soliton, and okay, so this is the same as this continuity condition. Well, okay, it's analog, and yes, and moreover, this function v, the velocity of the soliton, it satisfies some analog of this kinetic equation. Okay. Well, yes, okay. So as I already said, so the main point in the analysis, which if you want to capture the position of the soliton, it's not within with the jumps on this counter, on this part of the counter, but they are well, okay. So the position of the soliton is determined when these blue lines are intersect or close to this point I kappa 0. So at the point I kappa 0, we have some residue condition like this, and then okay, so in different regions of this K plane, function phi is either big positive or big negative, and so here we have this exponent. So when this exponent is small, then we understand that the residue condition is just negligible. Then when this function phi is negative, so this jump is very big, then by some procedure we can just revert. We can just flip the triangularity, and this exponent will go to the denominator, and again we will obtain some small pole condition. This will result in the phase shift of the elliptic wave, but in any case, this is the situation when we don't have the soliton. And the soliton, we obtain the soliton indeed when this parameter, well, when this term is of moderate size. Okay. Well, yes. Okay. And as a result, we get this kinetic equation for the speed of the soliton. Well, okay. So this is basically the results which we obtained, and then I just want to briefly mention like possible generalizations of this. So yes. Okay. So first of all, as I said, this MKDV it has solitons, it has elliptic wave, but also it has some breather solutions, which correspond to points of the discrete spectrum outside of the imaginary axis. Then also the MKDV equation, it might have solitons and breathers of higher multiplicity. So we can have breathers also of, well, okay, of the order 2 or 3 or even more. And then actually with those points, we can fill in some complicated curves in the complex plane, or even some areas. And well, okay, and this is what actually, well, in my understanding, what is done by Gennady L and Tovbis for linear Schrödinger equation. They have some different procedure of construction soliton gas. So they obtain it from finite gap potentials. Well, okay, so and this is another approach to construct the soliton gas. Yes. So thank you.
Thank you, Alexander. I see there is a question in the chat by Alex Tovbis, and I think it refers to your previous slide. So what is your function U of S in the equation for VSOL? I think that he's referring to the slide previous to the one you're showing now.
Okay.
No, a bit further. Alex, feel free to chip in. A bit further, like just the one just before your last one, your penultimate one, I believe it was. Okay.
Not here, right? Okay. Well, okay. So probably it's this slide, right?
Yeah, that one. What is U of S here?
Well, I think it's just a misprint. I think it should be this row of S. So it's kind of distribution of this distribution. Right. Well, okay. So this function rho, it satisfies continuity condition, which is satisfied by this distribution function, and then it appears also here.
Okay, but it's okay. And the function V, that condition, which you call the continuity-like condition, is not exactly that, because if you compare the two, they are not exactly the same.
Yes, exactly. Well, yes, you're right. So what we obtain something which looks similarly to what, which looks similarly to what you obtain, or, well, to your equations. Yes, but they're different, right? So they're different because, for instance, you have integral from 0 to infinity. We have, yes, on the other hand, we have an integral over this interval. So it's some finite integral. Yes. So actually, we cannot compare like.
No, that's not what I meant. I meant for continuity condition, you have, if you go there, it sits inside the derivative, right? In the original. So here you have a ratio of two partial derivatives, rho t and rho x. And over there, it's, if you go to the beginning of your slides, right, what the analog of continuity condition is a little bit different.
Yes, I agree. Yes, they're different. Yes.
I got exactly the same difference, right, in the NLS context. Yeah, so it should be that way.
Yes. Thank you.
You're welcome.
I see that Dennis has a question. Sorry, Dennis, then you're next.
Yes, thank you, Constanza, and thank you for the talk, Alexander. So in the movie you showed, with the soliton going through that wave train, how do you get that data? I mean, do you just take a constant jump Riemann-Hilbert problem, solve it manually, get the eigenfunctions, use an Darboux transform to insert a soliton based on those eigenfunctions, and then get a formula at t equals 0 for like, where does this, you are time stepping here, I guess, right?
Mm-hmm.
Where do you get the data at t equals 0?
Okay, well, yes, you're right. So it's not easy to solve, well, it's not easy to modulate this, right, situation. So what we did, well, okay, so what you can do, you can write a program based on this fast Fourier transform for the KdV equation in MATLAB, right? So you can do this when your function tends to 0 on both sides, right? Okay, so
yeah, that I know. I mean, but the question is, what's the formula you put in for the initial data?
Okay, yes. So
the
initial
time
data,
step.
yes, okay. So what we do here, we take again, well, we take the same code, but then we put somewhere inside we put this elliptic wave, right? So here, then on the far right, it will be, well, on the far right, we take 0. We just don't show this, right? But in any case, for finite, well, okay. So somewhere far from here, we take just 0. And then here we take solid, and then we just, okay,
so this is a linear superposition you are showing, actually, not the data coming from the solution of the Riemann-Hilbert problem.
Well, okay, so this is what you can obtain by solving by this fast Fourier transform method, numeric method, right? So, well, okay, I don't know, I'm not sure if it's a linear superposition.
No, that's not what I'm asking. I'm not asking, sorry, maybe I misspoke, but I'm not asking how you solve the KdV equation to do this movie. What I'm asking is, so there's a Riemann-Hilbert problem with 2 jumps on 2 cuts, right? And then there are 2 eigenvalues. That produces a potential at t equals 0. Okay. And that's supposed to be the initial data you put into the fast Fourier transform time stepper, right? But I think you're not putting that data in, right? Rather, you are putting a soliton far out and the elliptic wave far out. And there's some, okay, nonlinear perturbation coming in between, right? Because the equation is not linear. But if they are separated enough, it's okay, and you just time step. Is that what you're doing?
Yes.
So there's no Darboux transformation to construct the data here.
Yes, okay. Exactly. Yes, exactly
okay.
As you said. Yes. Okay.
Okay. Thanks.
Jenna?
Yes, thank you very much. Thanks, Alexander, for a very interesting talk. Well, I have a question. Well, it's fine that well exactly this slide. So, well, your soliton gas, well, as you presented, it looks pretty much like a one-gap solution. And the way you constructed it, it also kind of consistent, because you take an interval, you uniformly, well, I mean spectral interval, you fill it with solitonic eigenvalues, and this looks like a gap, like a band, sorry, to me. So, and this solution looks not very gaseous, I would say. It's just kind of, it looks like regular single gap solution, well, knoidal wave. So is it so?
Well, okay. So this is just in this illustration, right? Okay. So for the illustration, we indeed just took this one gap solution, as you said, and the soliton. But in the Riemann-Hilbert problem, actually, you can put not necessarily that simple. Well, okay, not necessarily that simple situation, right? Because okay, so okay, probably I don't have this the final Riemann-Hilbert problem. But okay, so what you have here, okay, so we have here these pole conditions, and then depending on how this gamma j, how we choose them, we can actually get some different potentials, right? So not necessarily uniform.
Yes, I don't understand that, but well, in this example, your gas is equivalent to one gap solution. Is it correct? Well, in this illustration, is there any difference between your gas and just one gap solution?
Well, in the illustration, yes, you're right. So in the illustration, it's just one gap solution, yes. But in principle, with this, you can construct something more complicated. And yes, and also the derivation for this, well, kind of kinetic equation, they don't depend on how many bands you have, and and what is this distribution function, right? So you can so those equations, they're obtained regardless of the particular situation.
Yeah, my second question is that all these kinetic equations are just identical to what we have in KDV, and of course the reason is that I think that these two equations are related by Mura transform. So,
okay.
So if when you consider situation, I understand that for MKDV we have much richer family of solutions, because we'll have positive, negative solitons, we have breathers and stuff. But for the situation that you when you consider all positive soliton moving on zero background and interacting with this soliton gas, which is in your case equivalent to one gap solution, this situation is, I believe, has one-to-one correspondence with KDV. So we can just extract all these results from KDV. Is that correct?
Well, I would say that, okay, yes, you're okay. So there is interesting thing about this MKDV and KDV, right? So so the Mura transform between MKDV and KDV, it exists when we take, okay, so there are two types of MKDV.
Of course.
So one with plus, one with minus, right? So when we have here minus, then we get this Mura transform for the KDV, right? But that MKDV minus, it doesn't have solitons. Here we have MKDV plus. So okay. So on this level, I'm not sure if it can be like, if we can correspond to that easily, like via Mura transform. So I would say not. But on the level of the Riemann-Hilbert problem, okay. So on the level of the Riemann-Hilbert problem, okay. So where is it? Well, okay. So on the level of the Riemann-Hilbert problem, they are very similar, and I would say that's why you obtain the same as for the KDV equation. So the Riemann-Hilbert problem for the KDV equation, it differs from this. Well, just in one piece is that for the KDV we take vector Riemann-Hilbert problem. Here we have matrix Riemann-Hilbert problem.
Okay.
But
thank you. Yeah. Okay.
Any other questions for Alexander? Okay, then if not, thanks Alexander and Irina again for this session's talk. So now we're going to have